At 10:33 on Thursday night, Eastern Time, a shadow touches the left edge of the moon and starts moving across it. That shadow is the Earth. It is about 9,000 kilometres wide where the moon runs into it, and it is shaped like a cone. For the next 3.5 hours, the moon slides through that cone. It does not go all the way in. At the deepest moment of this eclipse, a thin, bright sliver, a little under 7% of the way across the moon's face, is still sitting outside the dark heart of Earth's shadow, lit, and wrecking your night vision. That sliver is the most informative thing in the sky on Thursday. It tells you, to a fraction of a degree, where the moon was when it arrived. It is the reason this eclipse is not a total one. And it is the reason the whole thing is worth staying up for, which is not the reason you have been told. Because the object you are looking at on Thursday night is not really the moon. Every useful thing about this eclipse is information about the Earth. Start with the practical, because most eclipse coverage gets this wrong in a way that costs you the event. 5 moments matter, and they have names. The first is P1, at 9:23 in the evening Eastern, and if you go out and look at it, you will see nothing at all. That is not your eyes. At P1, the moon enters the penumbra, the outer, softer part of Earth's shadow, where the dimming is so gradual that the moon looks completely normal for most of an hour. People go out at P1, see an ordinary full moon, decide the internet has lied to them, and go back inside. An hour later, the actual eclipse starts without them. The moment to be outside is U1, 10:33 Eastern, 3:30 in the morning in Britain. That is when the moon touches the umbra, the dark core of the shadow. From there, the change is unmistakable. A bite appears on the left-hand edge, and it does not stop. Greatest eclipse is 12 minutes past midnight Eastern, 12 minutes past 5 British time. 93% of the way across the moon's face, dark and coloured, with the one bright sliver left over. Then it reverses. Last umbral contact at 1:51 Eastern, and it is over by 3. From the eastern United States, you get all of it. From Britain, the moon sets while still in shadow, 8 degrees above the horizon at greatest eclipse. Either way, none of it makes sense until you accept that the moon has never once been a source of light. The moon reflects about 11% of the light that hits it. 11% is not much. Worn asphalt reflects about the same. If you could set the moon down in a car park in daylight, it would look like a large, dirty rock, because that is what it is. It looks like the second brightest thing in your sky, because it is a large, dirty rock sitting in front of nothing at all, which means the moon has no light of its own to lose. Everything you have ever seen it do. The phases, the brightness, the colour on Thursday night, is sunlight that arrived, bounced, and came to you. The moon is a screen. That reduces every question about an eclipse to one question. Where did the sunlight go? At full moon, the moon is on the opposite side of the Earth from the sun. That is what full moon means. You see the whole lit face because the sun is behind you. And if the moon is directly opposite the sun, it is sitting in exactly the same direction as the shadow you are casting, which raises an obvious problem. There is a full moon every 29.5 days. If a full moon puts the moon behind the Earth, why is there not an eclipse every single month? Hold that question, because something about shadows has to be fixed first. Put your hand under a desk lamp. The shadow has a dark middle and a fuzzy edge. That fuzzy edge is not your eyes, and it is not the air. It is there because the lamp is not a point. It is a bulb with a width, and from anywhere in that border you can still see part of the bulb. The sun is a bulb with a width, about 1/2 degree across from here, not a point. So the shadow the Earth throws has 2 parts, and they behave completely differently. The outer part is the penumbra. Stand there, and the Earth blocks some of the sun, but not all of it. Part of the disk is still peeking round the edge, still delivering light. At the moon's distance, it is around 16,000 kilometres across. The inner part is the umbra. Stand there and the Earth covers the sun completely, every part of it. At the moon's distance, the umbra is about 9,000 kilometres wide, on a cone roughly 1.5 million kilometres long. So the P1 problem explains itself. At P1, the moon is in the penumbra, receiving slightly less light than usual, a dimming you cannot see by eye until it is a long way in. At U1 it reaches the umbra, where the direct sunlight stops completely. That is the edge that shows up. 2 parts because the sun has a width, which leaves the monthly problem entirely unsolved. Here is the number that solves it, 5.14 degrees. That is the tilt of the moon's orbit, not relative to the Earth's equator, which is a different tilt and a different argument, but relative to the plane the Earth travels around the sun on. That plane is the ecliptic, and it matters because the Earth's shadow always lies in it. The shadow points directly away from the sun. The sun sits in the ecliptic, so the shadow does too. Always. The moon's orbit does not. It is tilted 5 degrees out of that plane, so for most of every month, the moon is above the ecliptic or below it. When a full moon comes round, the moon is usually several degrees over the top of the Earth's shadow, or several degrees under it, and it sails past with nothing happening at all. Do the arithmetic and 5 degrees turns out to be enormous. Earth's umbra, seen from here, has a radius of about 2/3 of a degree. The moon has a radius of about 1/4 of a degree. Add them together. For any part of the moon to so much as touch the umbra, its centre has to come within roughly 9/10 of a degree of the shadow's axis, and it can be anywhere up to 5.14 degrees away. Under a degree, out of a range more than 10 degrees wide. Missing is not the exception. Missing is the default, and it is what happens at the overwhelming majority of full moons. There is a second, tighter limit hiding in that arithmetic, and it is the one that matters on Thursday. Touching the umbra takes 9/10 of a degree. Going all the way inside it, which is the only thing that makes an eclipse total, takes about 4/10. The window for any eclipse at all is narrow. The window for a total one is less than half as wide again. A tilted orbit crosses a flat plane at exactly 2 points. Those crossings are the nodes, and the line joining them through the Earth is the line of nodes. So an eclipse needs 2 things at once. A full moon, so the moon is opposite the sun, and the moon near a node, so it is down in the plane where the shadow lives. A full moon comes every 29.5 days. Arriving at a node does not care, which brings us to Thursday, and the number that explains the whole night. Roughly twice a year the line of nodes swings round to point at the sun. When it does, the new moon and the full moon of that period both land near a node, and you get eclipses, usually a solar one and a lunar one about a fortnight apart. That is an eclipse season, and it comes round every 173 days. We are in one now. The total solar eclipse that crossed Iceland and northern Spain on the 12th of August was the first half. Thursday's lunar eclipse is the second. Same node alignment, 1 new moon and 1 full moon apart. Not 2 coincidences sharing a month, but 1 piece of geometry seen twice. But the moon does not arrive exactly at the node. It arrives near it, and how near is a number called gamma, how far the moon's centre misses the shadow's axis by. On Thursday, gamma is minus 0.4694. That is a miss, not a large one, close enough that most of the moon goes into the umbra. But it is a miss, and it is why the moon does not go all the way in. 93.19% of the way across the moon's face gets covered. The remaining 6.8% does not. That is the sliver, not a rounding error and not a technicality, a direct, visible readout of the fact that the moon turned up a fraction of a degree off-centre. Had it arrived a little nearer the node, you would be watching a total eclipse instead. That is the last of the geometry. Everything from here is about light, and about why a rock sitting inside a shadow, receiving no direct sunlight whatsoever, is about to become one of the most colourful things in the sky. By rights, the moon should vanish. Inside the umbra, the earth is covering the sun completely, not partly. There is no direct sunlight in there at all. A rock inside the umbra ought to go black, drop out of the sky and stay gone until it comes out the other side. It doesn't. It turns red. And the reason is the most interesting fact in this subject because the answer is not about the moon. Two separate things are happening and almost everybody collapses them into one. The first is refraction. The earth has air, and air bends light. Sunlight that just grazes the edge of the earth, light that would otherwise shoot past into space and miss the moon entirely, gets bent inwards by our atmosphere, into the shadow. The Earth's air is behaving as a lens 13,000 kilometres across, filling a shadow that geometrically ought to be empty. If the Earth had no atmosphere, a totally eclipsed moon would be genuinely invisible, not dim, gone. That is how the light gets there. It says nothing about the colour. The colour is the second thing. To reach the moon, that light takes a very long slant path through the atmosphere, not straight down through it like noon sunlight, but the long way, edge on, through hundreds of kilometres of air. And air scatters short wavelengths far more strongly than long ones. Blue is thrown sideways out of the beam. Red carries on through. It is the same physics as a sunset, for exactly the same reason. So here is what actually happens on Thursday night. Every place on Earth where the sun is rising or setting at that moment, the whole ring of dawn and dusk running around the planet, bends its light inwards and paints it onto the moon. The colour is not the moon's, it is ours. Every sunrise and every sunset on Earth at once, projected onto a rock 250,000 miles away. You are not watching the moon change colour. You are watching our atmosphere from the outside. Which brings us back to the sliver and the practical problem with this eclipse. 6.8% of the moon's face stays outside the umbra all night, still in the penumbra, still receiving direct sunlight. And it will be, by an enormous margin, the brightest thing in the frame. Your eyes adapt to the brightest thing you are looking at, so that sliver will drag your adaptation towards it, and the red will look weaker than it really is. Cameras behave worse. Expose for the sliver and the red disappears into black. Expose for the red and the sliver blows out across your frame. Two honest answers. Look slightly away from the bright edge and let your peripheral vision do the work, because it is more sensitive in the dark, and bracket your exposures, accepting that no single frame is going to hold both. This is a real cost. A total eclipse has no sliver. The whole disk goes red together, and it is far easier to see and to photograph. Thursday is not that. But the last total one was in March. The next is not until New Year's Eve 2028, and the sliver is carrying real information, which becomes obvious the moment you ask what colour it is going to be, because nobody knows. It is worth noticing how strange the duration is. The total solar eclipse 2 weeks ago had a maximum of 2 minutes and 18 seconds. Thursday runs 3 hours and 80 minutes of partial phase, and a total lunar eclipse can hold totality alone for over an hour and 3/4. They are geometrically opposite events. In a solar eclipse, the moon casts a shadow onto the Earth, and the moon is small, so that shadow arrives here as a spot typically about 160 kilometres across, and at most about 270. It does not linger. At mid-latitudes, it crosses the ground at something like 3,500 kilometres an hour, which means the shadow of the moon outruns a passenger jet by nearly 4 times. You get 2 minutes because a narrow shadow crosses you very fast indeed. Stand 50 miles off the track and you get nothing but a partial. A lunar eclipse is the other way round. The Earth casts the shadow and the Earth is far larger, 9,000 kilometres across at the moon's distance, against a moon 3,500 kilometres wide. The moon has to cross something more than 2.5 times its own width at roughly a kilometre a second. That takes hours, and because the darkened object is the moon itself, there is no path of totality and nowhere you have to travel to. If the moon is up, you are already in the right place. That difference is starker than it sounds. Stand still on one spot on Earth and wait for a total solar eclipse to come to you, and the long-run average wait is about 375 years. Most people never stand in that shadow. A lunar eclipse asks nothing of you but a clear sky and the right night, and it gives the same show to half the planet at once. You can also look straight at it. No filter, no eclipse glasses, no projector, which the sun, at every stage but the totality of a total solar eclipse, never permits. Nobody knows what colour Thursday's eclipse will be. That is not vagueness. That is the interesting part. A French astronomer, André-Louis Danjon, got tired of eclipse reports that were nothing but adjectives and built a scale. 5 points, 0 to 4. 0 is an eclipse so dark the moon nearly disappears from the sky. 4 is a bright coppery orange with a pale blue rim. The same geometry produces all 5. What varies is not the shadow. It is what the light passed through on the way in. Every photon reaching the umbra has travelled the long way through our atmosphere, so anything in that atmosphere changes the result. Cloud along the sunrise and sunset line blocks some of it. Dust changes it. Volcanic aerosol changes it enormously. The clearest case on record is the total lunar eclipse of December 1992. 18 months earlier, Mount Pinatubo had put an enormous quantity of sulfate aerosol into the stratosphere. When the eclipse came, the moon was extraordinarily dark, down at the bottom of Danjon's scale, because much of the light that should have been refracted inwards had been absorbed on the way through. Sit with what that means. A volcano erupted in the Philippines, and 18 months later you could read it off the face of the moon. That is the argument of this whole video in a single observation. The colour of a lunar eclipse is not a property of the moon. It is a measurement of the Earth's atmosphere taken from 250,000 miles away, using the moon as the screen. And the colour is not the only thing written on it, the shape, for one. And that was read off it more than 2,000 years before anyone had a telescope. Watch the edge of the shadow as it crosses the moon on Thursday. It is a curve. Watch it at any eclipse, at any time of year, with the moon anywhere in the sky, and it is always a curve, and always a curve, of roughly the same tightness. Aristotle noticed that, and understood what it ruled out. A flat disk throws a shadow whose shape depends on how it is turned. Sometimes a circle, more often an ellipse, edge on a line. Only one shape casts a circular shadow from every direction, however it is oriented. A sphere. He wrote it down in On the Heavens. Since it is the interposition of the Earth that makes the eclipse, the form of this line will be caused by the form of the Earth's surface, which is therefore spherical. He established the shape of the planet he was standing on by looking carefully at a different one, because for a few hours during an eclipse the Earth draws its own outline in the sky. And if you were standing on the moon on Thursday, you would be watching the other half of the same event. From up there, the Earth would be sliding in front of the Sun. A solar eclipse seen from the Moon. The Earth would be a black disk about 3.5 times wider than the Sun ever looks from here, and around it, all the way round, an unbroken ring of red light. That ring is every sunrise and every sunset on the planet, seen edge on at the same time. And that ring is the light falling on you. The red on the Moon and the ring around the Earth are the same photons, described from two ends. So, Thursday night. Ignore P1. Go outside at U1, 10:33 in the evening on the east coast of the United States, 3:30 in the morning in Britain, and give it 20 minutes before you decide whether anything is happening. Greatest eclipse is 12 minutes past midnight Eastern, 12 minutes past 5 in the morning. British time, low in the west and setting. Look for 3 things. The curve of the shadow's edge, which is the Earth's outline, the colour inside it, which is our atmosphere, and the sliver, which is the Moon, telling you it arrived about 4/10 of a degree off centre. Then do the thing almost nobody does. Put a number on it. Danjon, 0 to 4. 0 is nearly invisible, 2 is rust red, 4 is bright copper with a blue rim. Whatever number you write down does not exist yet. Nobody on Earth knows what it is going to be, because it depends on what is in our air on the night, and the only way to find out is for somebody to go outside and look. That is the real reason to be out there, not the spectacle, the measurement. And if you miss it, the next total lunar eclipse is New Year's Eve, 2028, over 2 years away. Put your Danjon number in the comments on Friday and say where you watched from. I want to see how much the answers vary, because the variation is the data. And if this was useful, a like costs you nothing and is most of what decides whether anything like it gets shown to anyone else. Subscribe if you want the rest. There is a full-length version of the mechanism coming, and then one about the Moon itself.